Hello, my name is Julian Dörfler, and I'll be presenting some joint work with Markus Bleiser and Christian Ickenmeyer on the complexity of evaluating highest weight vectors. So first of all, I will be talking about the motivation and why we are even looking at highest weight vectors and why they're important. Then second of it, I will be talking about obstructing polynomials and what the highest weight vectors even are. Then I will show our algorithmic results, and afterwards I'll show that those are essentially tied with our hardness results. So first of all, let's talk about why highest weight vectors are even important. First of all, proving strong unconditional complexity lower bounds is really difficult, as all of you probably know, and that there are very few methods at the moment. And one big thing to possibly look at is the algebraic complexity theory, which is for example, containing the determinant versus permanent question that Valiant posed in 1979. Then Molmoli and Sohoni opened the field of the geometric complexity theory with the goal of proving the determinant versus the permanent conjecture. And the way they were intending to do that is using obstructions to prove lower bounds. There are two different types of obstructions here. One of them is the multiplicity obstructions, and one of them is occurrence obstructions. Occurrence obstructions are just a special case of multiplicity obstructions. You don't have to care too much for the specifics here, though, as this is not fully part of this talk. The important thing, though, is occurrence obstructions cannot separate the determinant from the permanent. Ickenmeyer-Panova and Burgesser-Ickenmeyer-Panova proved that in 2016. So it is important to now look at the multiplicities specifically. And how do you do that? You calculate a basis of highest weight vectors, evaluate them at enough inputs. That has been done twice so far from my knowledge, and we build on those methods and improve them and generalize them. The main contribution here then is to just systematically study the complexity of evaluating the highest weight vectors, which means both algorithmically and complexity and hardness lower bounds. So what are obstructing polynomials even? For that, we first need to look at tensors. Tensors, you can view them as just non-commutative polynomials if you want, where it's just we tensor different components, but the order is important. But it is also multilinear in each of the components. So we can always find such a base, we have such a basis, and we can always find a decomposition into it. Then the symmetric tensors are what we would call the commutative polynomials instead. So how do they relate here? We just take all possible permutations and make sure that all components appear in an equal amount. So all the possible permutations should occur of the first, the second component, etc. To maybe give a more clear example of why we can call those the commutative polynomials is, then there's this natural isomorphism between homogeneous polynomials and symmetric tensors. Specifically, we have m variables and c to the m, and the degree d here, the homogeneous degree d, is also the tensor degree d. And they relate by this nice relationship that xi1, xi2, xid just gets mapped to the sum of all the permutations of the components, which is just the symmetric variant of the direct tensor here. So as a simple example, to also make a bit more clear how we relate degree 1 homogeneous polynomials here to elements of c to the m. The first variable, we call this x now for simplicity, is just the first default basis vector. Y is just the second one. Then the symmetric tensor, x tensor y, plus x tensor y tensor x, plus y tensor x, which corresponds to x squared plus y, x squared y. And this is just all the symmetric variants for this occurring. This is different from the normal interpretation of non-commutative polynomials as commutative polynomials in the way that we require all of them to be existent here and not just one of them. So what is now an obstructing polynomial? Here we want to separate two varieties in SimDV. So varieties, if you don't have to concern yourself with them too much here, but you can think of them basically as just two sets of polynomials that behave nicely, for some definition of nicely. So and now a obstructing polynomial is a polynomial in the coefficients of these original polynomials, which means it is in sim n, sim d v. And the polynomial evaluates to 0 everywhere on x, but non-zero almost everywhere on y. And that now easily shows that y cannot be part of x, because if it's 0 everywhere in x, it obviously would have to be so for y as well, if y was a part of x. So let's give an example here, because that notion might be unfamiliar of polynomials on polynomials. So let's take a generic polynomial of degree 2 in two variables, which would be ax squared plus bxy plus cy squared. The coefficients here are a, b, and c. We now have a polynomial in exactly these coefficients, which is the discriminant b squared minus 4ac. And it is well known that b squared minus 4ac is 0 if and only if p can be written as a square. So this separates the variety of all homogeneous degree 2 polynomials in two variables from those that can be written as a square. The main goal now is we need to restrict those obstructing polynomials a bit further, because this still allows for a lot of different polynomials and makes it too hard to study. And one way to restrict them heavily is using highest weight vectors. And these can conveniently be encoded by linear combinations of Young tableaus. And we'll come to these two definitions of highest weight vectors and Young tableaus now. So a Young tableau has a shape, lambda, which is just a partition of numbers, and is now a left justified array of boxes, like this down here, where row I contains lambda I boxes, and each box contains a positive integer. We now have rectangular content m times d if the tableau contains the numbers 1 through n each d times. So going back to this example here, this is a Young tableau of shape 4-2, because the first row contains 4 elements, the second contains 2, and it has content 3 times 2, because that means the numbers 1 up to 3 each appear twice. There's a second important notion here, which is the semi-standard Young tableaus. A Young tableau is said to be semi-standard if the entries are strictly increasing in each column and non-decreasing in each row. So For example, this next one here is semi-standard of content 3 times 2, still with shape 4, 2. Well, this one up here is not semi-standard because 1 is less than 3, so it's not non-decreasing in each row. And a last notion that we need is symmetrized Young tableaus. We can obtain content n times d from a Young tableau of content nd times 1. So this means all the numbers just appear once. And we replace the first d entries by 1, the next d entries by 2, etc. So in this case, 1 and 2 get replaced by 1. 3 and 4 got replaced by 2s. 5 and 6 got replaced by 3s. And if two of these Young tableaus symmetrize to the same one, then we call them equivalent. And equivalence will, as we'll see later on, mean that they compute the same function, compute the same highest weight vector. So how do we get a obstructing polynomial now from these Young tableaus? Well, we can first look at a evaluation at a generic tensor. So not even necessarily symmetric, but any of them. And we look at it in a rank 1 decomposition. And we look at placements. Placement just means we take one of those linear forms and effectively place them on the tableau. But since linear forms could be the same, we have to do it more formally to the tuples of indices. But the placement is now proper if each block of d consecutive numbers receives one permutation of linear forms corresponding to the same rank 1 tensor. That is what we mean here. It can be any of them, but it has to be a permutation of them. And then to evaluate them, we take the sum over all of these possible proper placements and take a column-wise determinant. So how does this work? We take our example from the last slide here again, our tableau. We look at E1 tensor E1 plus E1 tensor E1 plus E2. And now proper placement. We do this directly with the linear forms here. We place the linear forms on the tableau. The linear forms corresponding to the first term, so to the E1 tensor E1, got placed on the first two numbers, because that's the first block of the consecutive numbers. The second block and the third block receive the second term, the second rank 1 tensor each, but still have a permutation inside the block. So now this evaluation, this singular term to this proper placement that we have here is now determinant of the first column. We have these linear forms, so these just give us directly a linear form, a matrix, which we can take a determinant of, times the second determinant. And now the third one isn't a square matrix anymore. But if it's not a square matrix, we just take the top left most square matrix, the biggest square matrix in the top left. So in this case, it would be just a 1 and another 1 back here. And this gives us a contribution of 1 for this evaluation, total evaluation, and all the other proper placements, of course, would give more. Okay, and there is one last thing. We've already mentioned it, equivalence of two Young tableaus. If two Young tableaus are equivalent, then they compute the same highest weight vector, at least once we restrict them to just polynomials. Also, we will use the SUMD notation and polynomial notation equivalently, depending on which one is easier to use here. But always just think of these as degree D polynomials in dimension of the many variables. So let's get to our algorithmic results. And we need a few more tools now to evaluate these highest weight vectors a bit more efficiently. The first is we have to look at what points do we even want to evaluate the highest weight vectors. Because taking an arbitrary point is hard to describe concisely. So one thing that has been used a lot in recent works has been the Waring rank. The Waring rank is just the minimum amount of terms we need to write a polynomial as a sum of powers of these powers of linear forms. And we now want to generalize this, as we think this is a bit too restrictive. We look at algebraic branching programs instead, in particular at non-commutative algebraic branching programs. And quick reminder, an algebraic branching program is just a layer-directed acyclic graph with a source and a sink, and the layers, the vertices, the edges only go from one layer to the next one. And each edge gets labeled with a homogeneous linear polynomial. And now the contribution, or rather what this ABP computes, is now tensored on each of the paths. So we take a path, for example, this path from source to sink up here, and tensor each of the components, which is exactly 1/3 x tensor y tensor x. The second path here is x tensor y with, again, a factor of 1/3. And down here, y tensor x with another factor of 1/3. So this computes this symmetric polynomial, the symmetric tensor in a non-commutative way. And that is the important thing here, that we look at them specifically in this non-commutative way that computes symmetric tensors. And this now, of course, corresponds to the polynomial x squared y, as we've already seen. A second example that shows why is this a generalization of the Waring rank is, let's take a generic point of Waring rank 2. We can now just split up the paths directly and put the linear forms on it and have just separate paths, one for each. And the width of this is always going to be at most the Waring rank. And this now, of course, computes L1 tensor L1 tensor L1 plus L2 tensor L2 tensor L2, and which is L1 cubed plus L2 cubed as a polynomial. So this clearly is more general than just the Waring rank. And we will allow evaluation at points with small algebraic branching program sizes here. There's one last notion that we need to look at, which is the one of associated graphs. A Young tableau of now the symmetrized ones, so content n times d, has an associated graph on n vertices. So for each number that appears in the Young tableau, there's one vertex, and we connect vertices I and j if and only if I and j appear in a shared column in our Young tableau. So for example, here, 1, 2, and 3 are all in the first shared column. So this forms this clique on 1, 2, and 3 here. 1 and 4 are connected because they share an edge, and then 2, 3, and 4 don't have an edge, each because there's nothing sharing here. Even if there were more columns with 1 and 2 containing both of those, there would only still be one edge. So this is not a multi-graph, it's just a simple graph. And to show that this can produce very complicated graphs as well, we can see both a clique and a fully independent set can both be produced. Of course, we can just use more columns for more edges. But even here, even with semi-standard Young tableaus, you can already produce a really high clique. Okay, so let's get to our actual algorithmic results now. Since all of these use the same notation, we split them up first and say the notation first. So the notation is n is always going to be our highest weight vector degree. So that is, for example, the degree of the discriminant. The degree of the point of evaluation, so the degree of the variety we're looking at, is going to be d, and the number of variables in that variety is going to be m. The number of rows is a very important measurement of the Young tableau, so we call this R. And the non-commutative ABP width is going to be W. If you don't feel comfortable with the non-commutative ABP width yet too much, then you can also look at this as the Waring rank. That is replaceable, as the Waring rank is always higher than the ABP width, or higher or equal. Okay, so the first result we have is we use the structure of the non-commutative ABPs and evaluate in W to the n plus R and polynomial in the rest of the parameters. The second, a bit more complicated but more important one of the results is now that the n is only polynomial. So the degree of the highest weight vector isn't necessarily the important part for how difficult an evaluation is. The important part, rather instead, is the width of a tree decomposition of this associated graph. So we can instead evaluate an O of W to the omega, which is the matrix multiplication exponent, times the tree width plus 1, and polynomial in the rest. So this in particular allows evaluation of highest weight vectors which have a really high degree, but still only have a small tree width. But again, as we've seen above, the degree of the highest weight vector can also coincide with the tree width, for example, on a clique. So if we have a lot of rows, the chance is high that their tree decomposition can be pretty big and have a high tree width as well. And the last thing that we note here is if you still don't like non-commutative ABP width too much or don't feel comfortable with it, it's also at most the border Waring rank. So this, to the best of our knowledge, is the first time there is an evaluation at points of small border Waring rank, in addition to just small Waring rank itself. Border Waring rank just being how well can we approximate our polynomial by points of low Waring rank. So let's now come to the actual hardness results at the same time, and you will see those are almost tight. So again, N, D, and M will be needed. So for reference, those are the highest weight vector degree, the degree of the point of evaluation, and the number of variables. The number of variables also directly gives a limit on the number of rows needed. So this, you can also read this as a number of rows of Young tableaus that are already hard. So let's come to our actual results now. Even at no restrictions, so it doesn't have to be a semi-standard Young tableau, and at only 2 rows necessary, we can already show NP, sharp P, hardness, and we can show that under ETH, the exponential time hypothesis, there is no 2 to the little o of n algorithm evaluating this. For the NP hardness and the ETH lower bound, this is also not just explicit evaluation, but already evaluating whether the highest weight vector is 0. So whether it evaluates to 0. Even that is already hard. And here M and D can both be constant, and the point of evaluation only depends on D. So it doesn't depend on the actual highest weight vector that is given. In case we want to show hardness for semi-standard Young tableaus, then we need a few more rows. We need 5 rows, but we can still show NP hardness and a lower bound under ETH. But the big difference here is that it's only a 2 to the little o of root n lower bound, which is also something that could be expected, as semi-standard Young tableaus, at least with 2 columns, have at most a tree width of root n, which is something we've also proven in this paper. So this is expected, and it would be rather unexpected to be able to improve this to 2 to the little o of n. In this case, we also have to get a bit of a higher Waring rank, but still only 5. So let's go over some general proof ideas here for this hardness. We recall the evaluation formula as the product of determinants over all proper placements, and we reduce from graph coloring. We will make a direct correspondence between proper placements that have a non-zero contribution to proper graph colorings that have no colors on the same edge. So we make sure that always one thing we use is the contribution of a placement which plays the same linear form twice in the same column is 0 because of the determinants, which will correspond to the same column being on 2 ends of the same edge. In Waring rank decomposition also, we notice that entries corresponding to the same block receive the same linear form in any proper placement. And if we double columns, we make all contributions positive by squaring the determinants so that we have always a positive contribution for each term and there are no cancellations. So let's look at this bigger example first, just to show the construction of these graphs a bit clearer. Whenever there is an edge between 2 vertices, we just have that column appear twice. For example, 1, 2 exists, the column 1, 2 exists twice. Or 2, 4 exists, and the column exists twice. This tail end here at the end doesn't have any contribution to the sum in the end, but this is just here, so we have that our total sum is this tail end here at the end is only here so that in total this is a rectangular content. It will not affect the actual sums that we have here, as the determinant of each of those linear forms, just a singular one alone, is just 1. Also, this point of evaluation can be is this exact point every single time, just to which power we take them, the linear forms will change. It's a small example, so we can actually show some placements. Is this 1, 2, 3? And we color code these as 3 colors because that is basically the direct equivalence to colorings. So we have the coloring, we place the linear forms directly on here. The first element got color 1, so color 1, the linear forms are placed on the 1s. Same for color 2 and color 3. And the determinants now you can clearly see are squared, all of them, including actually the later ones here. So this gives a positive contribution, specifically a positive non-zero contribution. But if 2 neighboring ones get assigned the same color, then those correspond to a proper placement where the same linear form is placed in the same column twice, so the determinant is 0. If we now want to This is a special case here where it's exactly 1. Some of those determinants could also be 2 or even higher, as you can see here. But if we choose the linear forms a bit more carefully and double up the rows not twice, but 6 times, and make sure that all of these determinants are 6th root of unities, then we get that the contribution is exactly 1 per term, and that gives us sharp p-hardness. And if we want to go to semi-standard contributions, semi-standard Young tableaus, then we just need more columns in order to encode the more difficult structure. So I'm looking forward to any questions on the talk afterwards, on the conference, and thank you for your attention.